In this video, we're going to be going over section 2.5 from our textbook, which goes over the piecewise defined function. So let's remind ourselves of the absolute value function that we talked about in the last section. And so this is a good example of a function that's defined by different rules over different areas of its domain. And so that is an example of what a piecewise defined function is, or just a piecewise function. So for example, this is the absolute value function that we just mentioned. And so this is a piecewise function because we have rules for our function for different regions of its domain. So for the absolute value function, we know that for values of x that are greater than or equal to 0, we're going to get that our function is equal to x. And we can see this by just looking at the graph of our absolute value function. So in this region, we have all positive values of x, and we're including x. That's why we have this closed circle here in blue. So for all values of x greater than or equal to 0, our output is just x. Y is equal to x. And then our second rule here tells us for all x values that are less than 0, we get minus x. And we can see that on this region of the graph as well. These are all x values that are negative or less than 0. And so this is what we get. Y is equal to minus x. So for example, let's look at another piecewise defined function. So we have our absolute value function again, and I'm saying that our function is equal to the absolute value if x is greater than or equal to 0. So this, in this case, this is my rule now. I'm saying this will be our graph if, or for all values of x greater than or equal to 0. And so we know all values of x that are greater than or equal to 0 are going to be in this region. So what we're saying is that in this region, we're going to have our absolute value function. So we all know our absolute value function looks like this. Whatever we input, we get as an output. So if we plug in 1 here, we get 1, we plug in 2, we get 2, and so on. And so this is occurring only in this region where x is greater than or equal to 0, so I'll put a closed dot there. And then our second rule here tells us that we're going to have f of x is equal to x squared if x is less than 0. So wherever we see that x is less than 0, so in this region here, these are all negative values of x, our graph will look like a parabola. So that means if we plug in 1 into x squared, we're going to get 1. If we plug in negative 2, we're going to get 4, and so on. So we have this parabola there. All right, so that's another example of a piecewise function. We're essentially just breaking our graph into regions based off of these rules here. So we're going to look at this next example here. So we have a piecewise function here, f of x, and we're told that for values of x that are less than 2, we'll get x minus 2 squared, and then for values of x that are in between 2 and 6, we'll get x plus 1. So the first thing we're asked to do is to find these values of our function. So the first thing we want to find is f of 0, and we know that 0 is a number that's less than 2. So when we're plugging x is equal to 0 into our function, we're going to use this guy here. So we'll get 0 minus 2 squared, which is negative 2 squared, which is equal to 4. The next one, we're looking at f of 1. So x is equal to 1 in this case. And here we also have that we're going to be using this guy because 1 is less than 2. Get negative 1 squared, which is equal to 1. Right, for the next one, we want to figure out what our function value is when x is equal to 2. So we're not going to be using this one anymore because this was the case only when x was less than 2. Looking at our next piece of this function, we have that for values in between 2 and 6 and including the value 2, f of x is going to be equal to this guy. So we'll plug in 2 into x plus 1, and we'll get 3. Similarly, for 4 is in between 2 and 6, so we're going to be using x plus 1. And lastly, if we want to look at f of 6, so x is equal to 6, we'll also use x plus 1, because we know that this is true for values of x in between 2 and 6 and including these numbers. So we'll have 6 plus 1, which is equal to 7. All right. Now what we can do is plot these guys. So something to note about our piecewise defined function, if you remember from the last several videos, we do have this power function. We have this x minus 2 squared. So this will just be our parabola of x squared shifted 2 units to the right. So you could just plot that in this region here. And similarly, we have the function y is equal to x, just shifted up 1 unit. So you could plot that in this region here. What we're going to do is, we will be plotting that, but we're also going to use these points that we just found to help us do so. So first, we know that when x is equal to 0, f of x is going to be 4. So 0, 4, we're going to put a point there. Then we also know when f is equal to 1, our output's 1. So we'll put a point here. Similarly, in this region, we know that x is going to be less than 2, so we're not including values of 2. We also know, like I said, that this is a parabola shifted 2 units to the right. So if this were just x squared, it would look like this here. We would start at the origin and move in this direction. But since we're shifting 2 units to the right, we're just going to move that point over 2 units. And since we know that x is not going to be equal to 2 here, we're going to put an open circle there. We can also test this just by plugging in points, and we will see that we'll get the parabola, or plugging in more points than we already have, and we'll get this parabola here. All right, now looking at x values in this region, so all of these guys here, we'll plot our line. Remember, it's just going to be y is equal to x, shifted up 1 unit. So at 2 we have 3, at 4 we have 5, and at 5 we have 7. Okay. And so we'll get a line that looks like this. It's y is equal to x, shifted up 1 unit. And we will be including these endpoints because remember, in this region, we have x plus 1 if x is in between 2 and 6, and including these values. So we have the closed circles here. All right. Now we should be able to find the domain and range of this function. And we can clearly see, even without looking at this graph here, what our domain is. We're looking at all values of x less than 2. So this will be negative infinity up to 2, and not including 2. However, we also have this region here. So all of these x values in between 2 and 6 and including 2. So instead of, you might want to write it like this. So we have negative infinity up to but not including 2, and then union this region including 2 up to 6. We can also write this as negative infinity up to 6. Now for the range here, we can see this just by looking at our output values. We're going to be from 0, but not including 0 because this is an open circle, all the way up to infinity here. This region is included in our range, similarly to how our 2 is included in our domain. So we can just write it as 0 up to infinity, all of these output values. Okay, so the next example we're going to look at is this piecewise defined function here. And in this case, we have 3 pieces. So if for all values of x less than or equal to 1, we have f of x is equal to this. For all values of x in between 1 and 3, and including 3 in this case, we have this constant function, this minus 3. So this would just be a horizontal line. And then for all values of x greater than 3, we have the f of x is equal to minus x plus 5. All right, so what we want to do is plot this given these rules here. So we can do what we did in the last example where we input a bunch of values for x and see what we get. But in this case, I know what these look like, right? We have a parabola that's just shifted downwards 2 units. We have a constant function, so just a horizontal line. This is y is equal to minus 3, or f of x is equal to minus 3, so it'll be a horizontal line. And then we have this minus x plus 5. And so this will just be, we know that our y is equal to x function is just a line going in this direction through the origin. And this minus is going to make it have a negative slope, so go in the opposite direction. And this plus 5 just means that that line is going to be shifted up 5 units. And then I will apply all of that in these given regions here. Yeah, so like I said, you can definitely plug in values for x and plot it that way. But in this case, I'm just going to use my graph transformations. So looking at our parabola, we know that our parabola will look like this. Kind of like this, I guess. But that parabola is going to be shifted downwards 2 units. So here will be my first point. My next point, I know with the parabola x squared is 1, 1, so here. So that point will be shifted down 2 units as well. So there. And then my next point is minus 2, 4, if my parabola was just x squared, but we're going to go down 2 units, so it'll be here. Okay. And so repeating that process, we get a parabola that looks like this. But remember, the region we're looking at is for values of x less than or equal to 1. So we also have to include what happens here at this point when x is equal to 1. So we know that with our parabola, if it were like this and not shifted up 2 units, when x is equal to 1, we get 1, so this point here. And so we'll just move that 2 units down, so 1, 2. So our final parabola looks like this, and it's including the value of x is equal to 1. All right. Now in the next region, when x is in between 1 and 3 and including 3, so in this region here, we have that f of x or y is equal to minus 3. So like we said, this is just going to be a horizontal line because y here is going to be equal to minus 3. So typically this would look like a horizontal line like this, but remember we're only getting this result in this region from 1 to 3 and not including 1. So minus 3 is about here and not including 1, so we're going to do an open circle all the way up to 3. All right. And lastly, we're looking at minus x plus 5. Remember, this is going to be a line that goes through the origin and then shifted upwards 5 units. So that means if we're going through the origin like this, we also want to look at our region, so for values of x greater than 3, so we're only getting this result in this region here. So if I have y is equal to x through the origin like this, I'm going to look at values in this region. So I'll look at when x is greater than 3, so I'll look at this 4 here, when x is equal to 4, and this will be shifted up 5 units. So this is shifted up 4 units, and then shifted up 1 more, we'll get a point there. repeating this process. So the next point we'll get would be 5 minus 5. So shifting that upwards 5 units, we'll get 1, 2, 3, 4, 5 units. So we'll get a line here. And if you start to notice a pattern here, our line looks something like this. And then we're also not including the value of 3 there, so we'll have an open circle. So it should be here. And our line will look like this. And then this is for values greater than 3, so this will continue on in this direction. Alright, so like I said, I just want to emphasize that you can plug in values for x here, and you will get the same thing. I'm just using our graph transformations. I kind of just wanted to illustrate how we can use those and why they're so helpful without having to plot a bunch of points like how we did in the last example. Alright. And the last thing we're going to do is look at this example. So we should be able to be given a graph here and provide the rule of the piecewise defined function for the graph. So this just means that we are going to provide our function. So it'll look like this here. So f of x is going to be a piecewise defined function. And if you notice, we just have 2 regions here. The first thing I see is that we have the absolute value function, and it looks like it's shifted up 2 units. So this tells me this will be our function. And then we want to look at the region where this is true. And it looks like we're going all the way up to negative infinity for our x values in this direction. So this is going to continue on in this direction. However, in this direction, it looks like we're stopping right here at the value x is equal to 1. So this is for all values of x that are less than or equal to 1. We have this closed dot, so it's going to be equal to that point. Okay. And then here, it looks like we have a constant function. We have a horizontal line at the point where y is equal to 2. So this tells me we just have 2. And it looks like it'll be in the region where x is in between 1 and 3, not including 1 because we don't have the closed dot, but it is including 3 because we do have that closed circle here. So this will be if x is in between 1 and 3, and including the value of 3 here. Alright, so that's why it is helpful to be able to recognize what kind of graphs we're looking at, absolute value, x squared, cubed, so on. And then also useful to know exactly what our graph transformations are so we can recognize this immediately and be able to write a function for it. Alright, so that'll be it for this video.